Okay, welcome everyone. Uh, can I just make sure that the people online can hear me? If you can send a message or something. Okay. So today's agenda will have a brief introduction, and then we'll have the presentations by the speakers. The speakers today were supposed to be Professor Barland, Dr. Stuart Hardy, and Hilary Shields. Unfortunately, Professor Barland had some personal issues, so he won't be able to join the today's session, and Hilary has kindly accepted to take on his presentation. So the presentation will end approximately at 7:30, and we will have, and this will be followed by approximately half an hour discussion. And following that, there will be food and drinks at East Side Bar. So the session of today is the second session of the MOGE discussion series. The topic of this session is fundamental principle of soil mechanics. The chapters of the MOGE that will be analyzed and discussed are chapter 14, soils as particulate material, chapter 17, strength and deformation behavior of soils, and chapter 19, settlement and stress distributions. This will be used as a starting point to go a little bit beyond the chapters and bring different point of view of the speakers. So the content of the chapters will be presented by Hilary, and after that, Stuart will put this concept into the context of what we do in the geotech engineering discipline. Big thanks to the sponsors of this series, which are Arup, Atkins, Realis, COE, GCG, McDonald, and RGI. And if any other companies are interested in sponsoring the future sessions, are of course more than welcome. So the idea of the MOGE discussion series is to have a platform to, as I said, start from the content of the book and, bring different points of view of the different speakers and also from the audience, and to have always a kind of an interactive discussion. And I would stress that the idea is this series is organized by the Early Career Group Committee, but the idea is to have the series open to professionals at all stages of their careers. As I said, today is the second session of probably 15 or 16 sessions. This is a mix of hybrid and there will be a mix of hybrid and online sessions. So far this is the second session, both the first one and the second one have been in London, but we will have, for example, the third one will be in Leeds, and the idea is to involve other territories apart from London. The audience participation in the discussion is very welcome. For the people in person, you can use the microphone or Slido, and for the people online, you can use Slido. The way you access Slido, you go to the website, you type Slido and you will find it, and you input the code 39083677 for your reference. The code will be on the top right of the slide for all the session. You can use Slido also for poles that will be activated at some point. So I'll leave the stage to Hilary, who will present chapter 14, 17, 19, and Hilary is Associate Director at 20G.
Sorry, Ricardo.
Yeah.
Can you help me with this screen just for a second? So I'm seeing the team
yes.
screen. Systems.
Okay. This is what you wanted?
Yes, that's it. And you've got the pen there.
Yeah, the laser pointer.
Yeah.
If you click on this. Okay.
Great.
Yeah.
Okay. Thank you everyone for coming and everyone online. I'm going to talk about the content of chapters 14, 17 and 19, as Ricardo's just explained. These chapters were written by Professor John Burland, and I can see that even though John has had personal issues which mean that he hasn't been able to attend, I can see that John's listening online. So John, I don't think people can see you, but I can see you, so thank you. The chapters are all written by Professor John Burland, and I'm presenting them really as a former student of John Burland, and also a connection from the time that I used to work in BRE Geotechnics and current connection with BRE Geotechnics. So just very quickly, just a very quick overview of John's career, which sort of has culminated with him teaching at Imperial College from 1980 to present. So that's 44 years. John studied civil engineering at the University of Witwatersrand. He returned to England in 1961, and he was one of the founding members of Arup Geotechnics, where he worked for a few years. Then he went on to Cambridge to do a PhD. And after he'd finished his PhD, he joined the Building Research Station in 1966, which was later called the Building Research Establishment, BRE, and where he became head of the Geotechnics Division in 1972. And in 1980, he was appointed to the chair of soil mechanics at Imperial College, where he's been ever since. And John Burland retired from full-time teaching in 2004, but he still continues to teach on the MSc course and assist in current research in soil mechanics and geotechnical engineering. And despite all his many years, he still attends Imperial College on a weekly basis. And I did the MSc course. I was one of the first people to do the industrial scheme, and I did it over 2 years. Actually, I missed the middle year because we were very busy at the time, but I finished it in 1996. And so here is a picture of John with 2 other former MSc students, Dinesh Patel, currently a fellow Arup, and Professor Jamie Standing, who is teaching at Imperial, and Stuart, who's going to come and talk after me. Stuart was also did both his undergraduate and PhD at Imperial and has been taught by John Burland. Because of the connection with BRE Geotechnics, where I worked from 1992 to 1999, there's a photo here of John Burland in 1970. I won't name all these people, but in this photo, there are 5 Rankin lecturers. And before this time, there were another 5 Rankin lecturers. So if you ever get hold of a paper by BRE, they're a fantastic source of detail and research, and really well worth reading. As you can see, the geotechnics division it ended in 2013 with the retirement of Ken Watts, but the ex-members, we still gather regular reunions. And it was at one of these reunions that John was telling me about how much work he'd done in proofreading numerous chapters of the MOGE, or whatever we call it, Manual of Geotechnical Engineering. And he was really, really supportive when the BGA Early Career Group decided to do a series going through the manual. So these are the three chapters. So why we thought that it would be good to have a session on these chapters is they really contain fundamental teachings, the basis for understanding soil behaviour, and I really think that if we can just keep these chapters in our minds, they'll give us the tools to really be able to handle a whole spectrum of problems we can come across in geotechnical engineering, and we can be versatile and not afraid of all the different things out there in geotechnical engineering now, if we just have this fundamental understanding of the way we expect soils to behave. The chapters also have references, so have a look at the references. So just to mention that time's very limited, so I'm going to have to go quite fast, but please do read the chapters after, and if it's helpful, go back through the slides. So firstly, chapter 14. This is about soils as particulate materials. And this is sort of a quote from the chapter, that the closeness of packing of the particles has a dominant influence on the mechanical behaviour of a soil. The more densely packed a soil, the greater will be its stiffness and strength, and the lower will be its permeability. So I was trying to think how to sort of illustrate an interesting aspect of thinking about the voids ratio. So firstly, I won't go through this derivation, but you end up that the voids ratio is the moisture content times the specific gravity of the soil. And so actually here the voids ratio is, here we see the volume of voids and the volume of solids, and the void ratio is the volume of voids over the volume of solids. I was trying to think of an example. I thought maybe you think about plasticity indices. So for instance, in saturated London clay, at the plastic limit, a moisture content of plastic limit, that's when the soil crumbles, and a moisture content equal to the liquid limit, that's when the soil flows. And in between the plastic limit and the liquid limit, the particles in the soil sample are held together by suction, because we're talking about a clay soil. Otherwise it'd be non-plastic. So if we think about it, sort of at the plastic limit in London clay, we've got a moisture content of about 25%, and that gives us a void ratio of 0.67, which means that 40% of the sample is voids. So here I've tried to draw this plastic limit with 40% of the sample of voids and 60% of solids. And I borrowed these pictures from Geolab's website of someone carrying out the plastic limit test, so the threads crumble. And then if we go to the liquid limit, at the liquid limit in London clay, the moisture content is about 70%. So that means the void ratio is 1.89. So at the liquid limit, about 65% of the sample is void. So I was trying to show over here that this is the comparison between the liquid limit and the plastic limit. So here we have 65% of the sample is voids, and I was trying to illustrate clay, so I've drawn little thin particles, and I have no idea if these particles have the same number as these ones, but they should be. And I was trying to show that basically the soil, which expands to fill this whole volume here, is compressed to fill a much smaller volume here. And so as the particles move together from here to here with decrease in moisture content and hence decrease in void ratio, the strength increases. And strength increase between the liquid and plastic limit is approximately 100 times. So then the chapter comes on to talk about particle size and shape, which is hugely important. And it has this well-known particle description of the sizes of different particles through from sort of boulders, gravel, sand, silt, clay, organic soils and peats. And it tells you what you should comment on when you're describing these samples. It also has a picture of the different sort of shapes of sample you expect to see. So here we have clays at the top and granular materials in the middle, and so it goes on. And it also tells us the sort of surface area that you have for the different types of particles. And one thing you can see immediately is that for a given mass, the surface area of clay particles, and these are different clay mineralogies here, are much larger even than the next size up, which is fine silt. So key things pointed out in this chapter is that the shape and angularity of the particles have a profound influence on the shearing resistance. You know, and we know that intuitively because we know that a rounded surface will have less frictional resistance than a rough surface, for instance. And clay particles are much smaller than granular particles, and they're usually plate-like in shape, and they have tiny voids in between them. So although you might end up with the same void ratio as a granular soil, you've got many, many more particles, and the voids are and many, many more voids, and they're all tiny. And the mixture of particle sizes, you know, all the way through from the, you know, the clays through to the gravel, gives what we call the grading, and it defines the soil type. And the clay content in the soil, together with its stress history, has a dominant influence on its strength and compressibility. And the proportion of these tiny voids from the clay content, as that increases, the permeability decreases, and you also get increased surface tension between the particles. So coming back to that, to thinking about plasticity, so we define the plasticity index as the moisture content between the liquid limit and the plastic limit. So a lower plasticity soil has a lower clay content than a higher plasticity soil for the same clay mineralogy. And that means it, on average, it has bigger void sizes. So the thing about a lower plasticity soil is it needs less change in moisture content, i.e. less change in void ratio, to take it from its plastic limit to its liquid limit. So we can see that for a given change in stress, the change in void ratio is smaller for a lower plasticity soil, and therefore the lower plasticity soil is less compressible. Then the chapter goes on to talk about the effect of gravity on soil strength. And here, if you look online and Google John Berlin Bare Essentials of Soil Mechanics videos on YouTube, you can see some photos he's put together, videos of fundamental aspects of how soils behave. And these pictures, there's this a base, it's called a base friction apparatus. It simulates the effect of gravity and pulling particles downwards. And these three photos sort of show the particles being deposited under gravity and gradually building up, and the sort of structure they build up at the end. And so what he's pointing out is that this process of deposition, what you find is that the particles form into clusters, and you get arching around the voids. So some, for instance, here, some particles are stressed, and then particles underneath the arch aren't really doing very much at all. And you get numerous vertical and subvertical columns of particles. So you could trace a column of particles going up through this material. And so he's making the point, in this normally deposited soil, the structure is stiffer and stronger in the vertical direction. And this has an important implication for normally consolidated soils. For instance, many clays develop bonding on these contacts, which can break after a small strain, and the structure then collapses with further shear strain. And when the vertical stress is reduced, the material is defined as over-consolidated. And it's important to remember that the vertical stress can reduce, but the horizontal stresses can't reduce as much. So the horizontal stresses start to become locked in. And eventually this leads to a material that's stiffer and stronger in the horizontal direction. So then the chapter looks at contractant and dilatant behaviour. There aren't pictures of this, but I've tried to illustrate that if you could, well, you can, in this particular apparatus, rotate the sides by the same amount. You apply simple shear to the sample. And what is observed is that when you apply simple shear to this sample, all those arches become broken. Sorry, I've superimposed this on the sample that wasn't sheared. But anyway, as you apply shear, the arches become broken and the particles take on a closer packing, and that's contractant behaviour. I've snipped these from Malcolm Bolton's Guide to Soil Mechanics in 1987. There are these photos of the particles, the volume contracting and the particles moving closer together. And then the chapter goes on to describe that if you tamp this top plate under gravity, so you're basically densifying the sample, the arches break and the soil becomes denser. And then when you apply simple shear to this sample, the volume increases because basically the particles now have to ride over each other as you push them sideways, as we can see in this diagram here. And as we discuss later, for a given effective stress level, the soils try to change in volume when they're sheared until they reach a critical state void ratio, it's called, where the soil will shear at constant volume. And so really, when we sort of, having thought about how the soil behaves, we can see that this critical state void ratio, it sort of represents a soil which is in a loose state, but it's after some shearing has broken those initial columns and arches, and so you've got more of the particles carrying stress to provide friction to resist that shear force. And the chapter then has a quick look at active and passive pressures, because in this base friction apparatus you can rotate the sides, and so if you rotate the side of this apparatus outwards, you can see an active wedge developing, and if you rotate it inwards, you can see a passive wedge developing. And what we see is that the passive wedge extends much further from this rotating wall than the active wedge, and much larger rotations are required to mobilize the passive earth pressure than the active pressure in general. And this is a snip from BSEN 1997, showing you the fact that you do need less rotation to mobilize active pressures than passive pressures. But just to remember that that's not always the case. So for instance, in a heavily over-consolidated clay, you've already got a high K0, and in this instance, the displacements to mobilize Ka and Kp are similar. This is from TRL's RR359 report written by Ian Simmons. So then thinking about foundation settlement and bearing capacity and what happens to the particles. So in this base friction apparatus, and these are stills from the videos that John made. So if you have a lightly loaded footing, it will come to rest, it will sink and it will come to rest when these particles have mobilized sufficient resistance to restrain that. If we then push the footing further, we fail the soil in bearing capacity failure, and that's when the soil can't resist, can't provide any more frictional resistance to resist that loading. But just to remember that for this footing to fail, what actually has to happen is that the soil has to move outwards and upwards. So it's actually the passive resistance in the ground that's governing that bearing capacity. And you can actually understand that if you think of a footing sitting at the top of the slope. You know, we know that if we cut away this soil here, we've got a much lower bearing capacity than, you know, if we're sort of sitting on level ground. And then after the footing has plunged, it will come to a new equilibrium, which is sort of illustrated by this sort of heavier footing here. When, because of the weight of all this material here, that has increased the friction on the particles underneath the footing sufficiently that this footing can, this weight of this footing can now be resisted by friction on those particles beneath it. So then the chapter goes on to describe the concept of effective stress in saturated soils. So here we have a little small volume of soil, and in that small volume we have the pore pressure U that acts in all directions, and the balance, which is sigma V minus the pore pressure and sigma H minus the pore pressure, and the shear stress, they are carried by the soil skeleton. And Terzaghi in 1936, with his principle of effective stress, defined that sigma minus U and tau, the shear stress, as effective stresses, and that all measurable effects of a change in stress are exclusively due to change in effective stress. Note that a shear stress is always an effective stress because water can't carry shear. And so John makes the point that it's important to note that the effective stress principle says nothing about the way the effective stresses are transmitted through the soil skeleton. So it gives no information on the stresses at the particle contacts, which we see here. There's an example of a loose granular material that's compressed by this all-around spherical stress. And so the relative movement between the grains can only happen because you get slip at the particle contacts, and then you get a closer packing of particles. But it's interesting. So we know that the change in by compressing this material with spherical stress, we know that's not going to change the shear stress. But we do know that there's shear stresses between particles, and what's happening is that all these shear stresses, they're acting in all different directions, so that ultimately the net effect is no external shear stress applied to this sample. And then almost at the end of this chapter, and we talk about drying and wetting of a soil. This is quite interesting because so basically, so if you think about it, for a saturated soil to dry, and this is illustrated in these diagrams. So at first, as the water content reduces because it's drying, the soil is still saturated, but the water content is reducing, so the pore pressure reduces, and the effective stress between the particles increases. And then as you carry on drying, this still saturated, and you get little menisci forming due to surface tension at the particle contacts. And actually, this is what means that pore pressures can become negative in soils. It's because of those surface tensions. So again, the effective stress still increases and the volume reduces. And eventually, at a suction limit, air starts to enter the pores of the soil. Lenses of water at the grain contact points, they generate interparticle stresses, and that's what allows a damp soil to stand. So here's a picture of John Burland in his YouTube videos with his little sort of sandcastle made with a plastic beaker, to illustrate the point. And then basically the void ratio remains constant as air replaces the pore water with further drying. In Malcolm Bolton's Guide to Soil Mechanics, he says that it's rare for the minimum void ratio of a clay after drying to be less than 0.35 or above 0.45. Yes, so this surface tension is what enables pore pressure in clay soil to go into suction when the soil is unloaded or where it's sheared undrained. And so then the process of wetting a soil, when you're wetting a soil, basically you can imagine these stabilizing forces, the grain contacts are removed, and that results in loss of strength and a reduction in volume, often called collapse compression. And then for a clay soil, you know, if it's dried, you've got shrinkage cracks. Water can get down those shrinkage cracks and cause the clay to swell as the surface tensions are removed and the effective stress is reduced. And so finally, just to mention, so our chair, Ricardo, he's done a fantastic PhD and written papers looking at how we can use the behaviour of partly saturated soils in sustainable sustainable issues like in mitigating climate change effects on slopes. So I've just snipped a drawing from a figure from one of his papers. So basically, obviously Ricardo can tell you far more, but there's a stability of slopes, in particular those made of fine grained materials with low angles of friction. It's often guaranteed by the presence of suction. And the most common cause of slope instability is intense or sustained rainfall. So this is something called a capillary barrier system, which people are looking at, researching and starting to use as a means to mitigate the impact of heavy rainfall. And this coarse layer, it's maintained at a very low saturation and very high suctions. And so that prevents water flow through it up to a certain volume that wants to enter it. And if you put this finer layer above it, the idea is that all the effects of rainwater and evaporation all happen in this fine layer, and this coarse layer is acting as a barrier to protect the natural soil underneath. So then we come on to chapter 17, Strength and Deformation of Behaviour of Soils. And this chapter really is like a sort of a journey through soil mechanics. So firstly, it talks about the Mohr's circle. So, you know, as we know that the Mohr's circle informs on the shear stress and corresponding stresses on all planes around the Mohr's circle, and helps us to think about what happens when we apply shear. And I was thinking how could I illustrate this? And I was thinking that we've got this familiar situation where in an over-consolidated clay soil, we know if the soil is strong enough, we can cut a vertical slope and the soil will stand there for a period of time and support itself. We would draw a Mohr's circle, which has the vertical total stress here. And we would know that if it had sufficient shear strength, which we see as the radius of our Mohr's circle, then the horizontal pressures could drop to active. And we know the expression that the active horizontal pressures are equal to the vertical total pressures minus twice the undrained shear strength, which is the radius of the Mohr's circle. But when we come to look at this, we can see that, and I was trying to draw proportional forces on a little cube of soil on the failure surface. 10 minutes. Oh, I've had 10 minutes. Yeah, okay. No, still have. I still have 10 minutes. Oh, I have to go very, very fast then. I'm sorry I've taken so long to go through that. So that took half an hour, did it? That took half an hour. Oh. Okay. Okay. Right. Okay. So basically, you can see that because the lateral stress has been reduced here, the soil wants to develop shear stress to provide a component to resist the out of balance earth pressures out here. And you can see that if we resolve these stresses we'll arrive at the fact that the horizontal stress is sigma v minus cu sigma v minus 2 cu. So, and then there we have to get the drain strength of soils, the Moore-Coulomb failure criterion. So this defines the criteria for when the soil will fail, when a plane in the Mohr's circle becomes tangent to this failure criterion, which is that the shear strength is equal to the C dashed and the normal effective stress times the tan of the angle of friction. And so just to say that this is a construction to fit those Mohr circles, and in fact this C dash is a construct. You really only exists, a C dash really only exists in practice if you get interparticle bonding at very low confining stresses, and generally don't rely on that. And just to make the point that we represent the development of progressive stress through Mohr's circles by we can plot the center of the Mohr's circle against the peak stress in the Mohr's circle, and so we can illustrate how the stress state in the soil changes as we shear it through this stress path. Just because originally when people started to investigate the behavior of soil in shear, they knew that they had a direct shear apparatus where they wanted to apply a shear stress to a plane with a known effective stress. And what we try and do in this test is the idea is that we have a given normal stress here. We apply a shear stress and we see the angle of friction on the failure plane. The assumption is the failure plane is constrained to the horizontal plane. The thing about this test is we don't measure sigma h dashed in the direct shear test in any direction, so the spherical conditions are not known. And the strains around the failure plane are highly non-uniform, so the volumetric strain isn't known either. So working at Cambridge, Roscoe in 1953 developed a simple shear apparatus. And the idea was that you could apply uniform strains to the boundaries of the samples, and you could understand what the change in void ratio was as you sheared the soil. The thing about this apparatus is actually it doesn't constrain the soil to fail on a particular plane, but nevertheless, you can understand the principles of what's going on as you shear the soil. So here we have four granular soils at different densities. So this number 1 is the loosest, number 4 is the densest, and as they get sheared, they change in volume, and the loosest sample you'll see will contract during shear, and the densest sample will dilate. And as they dilate, they reach a peak strength at a maximum change rate of change of that volume, and then because you can these are strain control tests, you can measure the strength fall off until the soil fails at constant volume at what we call the critical state void ratio. And so this peak strength is controlled by the initial density. So here we can see shear stress against effective stress. We can see the peak strength is highest for that most dense sample and least for the loosest sample. And if we had a higher pressure, we would see higher peak strengths. And these envelopes are curved. And the point is that for all these samples, for a given level of effective stress applied in the shear box, they all converge to the same void ratio, which is called the critical state. And the critical state line is straight and it passes through the origin on the MERS plot. The peak strength is due to this dilation effect. And we define the peak strength as a constant volume angle of friction and an angle of dilation. Just to mention that many design situations we're using the peak angle of friction, which comprises of that constant volume angle of friction and the angle of dilation. And this constant volume angle of friction is the function of the soil mineralogy, so the particle strength, as we already discussed, the particle angularity, and also the particle grading, because with a better graded sample, a bigger range of sample, each component increases that basic frictional resistance at the critical state void ratio. And then this angle of dilation depends on the relative density, the particle strength, because particles can crush as well with granular materials, and the stress level. And you can go to BS 8004 and other UK codes and guidance, and you'll find equations that take you through exactly that thinking. One thing that's is noticeable is that the plane strain angle of friction of dilation is greater than the triaxial test. And that makes sense because in the triaxial test, the soil can change in volume in 3 directions, whereas in a plane strain, it can only change in volume in 1 direction. Then the chapter talks about the shear behaviour of clay soils, and we see that the normally consolidated behaviour of a normally consolidated clay soil is similar to that of loose sand, i.e. it contracts to a critical state. But an over-consolidated behaviour, so with the over-consolidated soil, here we see it's been compressed along the virgin compression line, and then it's been swelled back to its over-consolidated state. So now this is void ratio against effective stress, and you can see that for the same effective stress, the void ratio of this over-consolidated sample is much denser than its normally consolidated counterpart. And as you shear this dense, effectively what's a dense sample, it will reach a peak just like the sand did. But then what we find is that it misses that critical state that it's aiming for, and the particles start to align, and it starts to get progressively degrade in strength until it reaches a residual strength. There's a diagram with plasticity index here, which shows how the critical state angle of friction reduces with plasticity index, but how for a normally consolidated soil, but for an over-consolidated soil, we see the angle of friction dropping off below that critical state angle of friction. You said it now? Okay. So undrained strength of clay soils. So I'll just this is quite an important slide. So basically, what happens with an undrained soil when it's sheared undrained? So in a dense condition, so the soil would want to dilate, but it can't dilate because it's prevented from doing so. So what it does is it generates negative pore suctions as it's trying to increase the effective stresses to get to the critical state. So the pore pressures go into suction, and the effective stresses increase as the soil tries to reach critical state. But note that typically the suctions can't be sustained, or natural defects like fissures come into play, and the strength can't reach that critical state. But you can imagine if you allow drainage to take place at a point like this, and so the soil drained to its vertical effective stress, the soil couldn't sustain that shear strength and it would fail, and that's the cause of long-term slope failures. Whereas the normally consolidated soil, it wants to contract, but it can't contract, so it generates positive pore pressures, reduces the effective stresses reduces as it heads for the critical state. But there is an important point about normally consolidated soils is they often have got some bonding because they've aged and they've become bonded, and then you can get a sort of a much more brittle failure, and then the effective stress because of that, because the bonding breaks, and then the effective stresses can reduce quite rapidly afterwards. I won't go through this slide, but just simply to say that undrained shear strength is not a fundamental property. It really depends on the degree of overconsolidation, the plasticity, the bonding, the mode of shearing, the rate of shearing, how we sample the soil, and the sampling disturbance. And it is simply the peak strength that you measure in whatever test you're doing. And that will vary depending on all these factors. And then the chapter goes on to talk about the one-dimensional compressibility of soils. You can read this chapter, but basically we see that as the soil is compressed, it becomes more stiffer and stiffer, less and less compressible. But the particles are basically slipping past each other, and what happens is that slip, it's irreversible. So when we unload the soil, we don't recover. And we don't recover its initial volume, and we have a stiffer behaviour on reloading. And this was really just to show you what happens with London clay. Basically, that here is our London clay being normally consolidated, and then as it's become unloaded in geological history, those effective stresses that we mentioned have become locked in, and eventually you end up even near the surface in a state of passive failure, and the soil has become a lot stronger and stiffer than it was during normal consolidation. It's also stiffer in the horizontal direction. So just very, very quickly, so a real soil, so this is a virgin compression line of a reconstituted soil where the soil's been broken down and remixed and being reconsolidated. And if you pause that, this is what happens to a real soil, it will creep. And then if you start to reload it, the soil will have established some bonding, and it will move over to the right of the virgin compression line before those bonds break, and it starts to head down towards that virgin compression line. And there's some in John Burnham's Rankin lecture on the compressibility and shear strength of natural clays, there's some great plots of the void ratio against the vertical stress for different clays. And actually this is interesting because you can see that there are the lines for increasing liquid limit. And if you remember, we were saying earlier that the less plastic a soil, the less compressible it will be. And we see that here, that as the soil is becoming more and more plastic, so the compressibility is increasing. And what you find is when you normalize these curves, this is the intrinsic soil behavior, and this is the behavior of the natural clays, the sedimentation compression curve that John Burnham called it, lies over to the right of the intrinsic curve. In other words, for a given void ratio, the natural soil is stronger than its intrinsic counterpart. And if you do an odometer test, you'll find that the material moves out and then heads down. And I think I had better just whiz through the slides, just show you them and then stop. Go through idealizing the soil as a linear elastic behavior. We go through the triaxial test. I had a little slide that perhaps you can have a look at, which basically what happens to an ideal soil when you sample it. And I just really wanted to make the point that whilst this is the total stress circle in a quick undrained triaxial test, the soil is really failing on an effective stress circle back here. And for a while, I asked myself, how does the soil know which plane to fail on? How does it know it's undrained? How does it know it's drained? And the point is that if you will use the right stress, if you decide it's going to fail on a 45-degree plane, use the undrained shear strength. If you actually knew its effective stresses in that undrained condition, and you would use the effective stress on the failure plane, then you have to use the right failure plane, and you'll get the same answer. Right, okay, that's it. I'm sorry. I was going to describe that real soils obviously are not linear elastic. They are non-linear stress strain behavior. Stiffness depends on the confining pressure, and you get effects of anisotropy. So there we are. I'm out of time, but thank you for listening. We'll hand over to Stuart.
So you can have a quick look at these. Two more slides on the recording. So just quickly, you can start adding your, asking your questions on Slido, and there's also an active poll on Slido. It's all anonymous, so feel free to respond, honestly. And so you can access this from here, and I'll hand over to Dr. Stuart Hardy, Associate Director at ARU.
Thank you, Ricardo, and thank you, Hilary, for the great session already. That was Hilary's far too modest to mention, but this whole series of talk was Hilary's idea. So I think we all owe Hilary a huge thank you for that. And of course, the Early Careers Group have done a great job of setting this up. So thank you, Hilary. It's an exceptional engineer and human being. We deserve enormous credit for it. So, as Ricardo said, I'm Stuart Hardy. I'm recently rejoined the Arup Geotechnics Group in London after a dark walk on the dark side. I'm just want to talk about my experience over the last 21 years or so of dealing with these displacements, taking some of the fundamental ideas that Hilary talked about and John Berland wrote about and what they mean in modern geotechnical engineering, and perhaps a little bit of future gazing about what may happen to us as engineers, geotechnical engineers in the future. So as Hilary talked, we need to go back to the principles. We need to understand that soil is a particulate material, how it forms, how it behaves. And then once we understand its particulate nature, we can then start to categorize its strength and its deformation behavior. And then we can start to do some calculations about settlement and stress distributions. But of course, these are on a very micro level. This is understanding particle level or soil sample size behavior. What I want to take you to the next step is to go to the meso level and talk about how we use this information to look at individual structures. And then on the macro level about how we can pull together individual structures into one whole project of any size. So that's the outline of my talk today. I want to discuss quickly about why are ground movements important? Why do we need to sort of calculate them and consider them? Very quickly, I'll talk about why do they occur, but I think Hilary's done a very great job of explaining about why movements occur. And then we're going to go on a little bit of a story from geotechnical history of how they've been dealt with through the evolution of geotechnics as a discipline. How we started with strength-based approach and linear elasticity, how empirical methods evolved as monitoring improved and case history data was published, then the advent of numerical analysis and what that can do, and then, as I said, a little bit about the future. So starting on about why they're important. Well, this is not great, but it's the reality. We have to comply with codes of practice. And in the UK, of course, we follow Eurocode 7. And there's clear sections 2.74 in that document that tells us we need to consider the ultimate limit state of structures in their designs. So that's about safety, about preventing collapse, and things like that. And we consider the loss of equilibrium, structural failure, or geotechnical failure. But the very next section, 2.48, tells us that we also need to consider the serviceability limit state. And serviceability is not about collapse or safety. It's about appearance, it's about function and comfort and things like that. And just to put that in context, the ultimate limit state looks a little bit like that. There's an example of a gravity retaining wall failing due to the snow melt in the Austrian Alps. And of course, most famously, the collapse of the Nickel Highway structure in Singapore, which resulted in the death of 4 workers, unfortunate souls at the bottom of that excavation. So clearly we need to prevent that happening. That's the ultimate limit state. But we also need to consider the serviceability limit state, as we said, and that could be of the structure itself. And there's a rather trivial example in the top figure there of a garden wall. Clearly that wall hasn't fallen over, it hasn't collapsed, but it looks pretty bad. And you wouldn't feel perhaps happy having it in your driveway. But we also need to consider the serviceability limit state of neighbouring structures. So this poor guy, he's got a lovely house, it hasn't collapsed, he can still live in it, he can still sleep in it safely at night. But it's pretty embarrassing to have a 20mm crack in your front wall, and it's clearly not serving its function anymore. So it's a serviceability limit state, and it's displacements that feed into the assessment principally of the serviceability limit state. So it's in the codes of practice. That's the first reason. Second of all, it's often, if you're working on large projects, written into the specification for the works. Many people in this room, I'm sure, have worked on HS2, and there's clear statement in the document that the construction of the proposed work will require a range of underground works, including tunnelling, and this document sets out how you should assess those, and as far as reasonably practical, mitigate those movements. So it's in the codes of practice. Our clients require it often in their technical standards and their requirements to us. But it's also a little bit about professional reputation and industry reputation. If we go around constructing new buildings, infrastructure, whatever, and damaging people's properties or damaging utilities and things like that, then it's not great for our industry or our professional reputation. So codes of practice, works information and technical standards, but also it's the right thing to do for our industry. So they're clearly important to what we do. So why do they occur? And this will be a quick run through what Hilary sort of talked about. So they occur in retaining walls. They occur around retaining walls. It's fairly trivial and evident that if you embed a retaining wall in the ground, you excavate in front of it, the wall moves into the excavated area. The soil on the back of the wall goes into something close to its active state, and the wall ground in front of the wall goes to the passive state. And as the wall moves out, the ground goes down, and anything behind it is clearly going to be affected by those displacements. Tunnels. It's impossible to wish a tunnel into place magically. There is a process of the tunnel boring machine going through the ground, removing the soil, some stress relaxation before you can put the lining in and grout the gap up and hopefully prevent any more movement. So as that stress relaxation occurs, the ground relaxes, and of course the surface ground also settles in response to that, affecting anything at the surface. Foundation loading, as Hilary showed with the John Berlin video, if you put a load on a footing, of course it's going to settle, and it's fairly obvious. We also have substantial movements and large zones of influence due to water extraction, due to dewatering. And that's, of course, removing the water from the soil, reduces the water pressure, which increases the effective stress, which then causes settlement to occur. So these are sort of four main areas of movement, causes of movement in engineering structure that we often consider. But how do we go about assessing these movements? So in essence, this is the geotechnical timeline. I'd be like this, I started in 1900 and went through to the present day. I think that's about right. But if we think about a simple footing problem, the solution to this problem comes from Prantl in 1920, and he was considering the penetration of, I think, projectiles into sheet metal. And he found a relationship for what was essentially a plane strain problem. We're all familiar, I'm sure, with this equation. He said that the ultimate capacity of an infinitely long strip footing is the width of the footing times 2 plus pi, which sounds frighteningly accurate, times the strength of the material, which we would, in soil, would call, for a clay material at least, the undrained shear strength. So, in essence, he didn't consider settlement at all. He found the ultimate capacity of the strip footing. We then fast forward a few decades and we find Skempton, whose building we're standing in at the moment. He made some slight improvements to that equation. He added 2 further factors. the shape correction factor, which allowed us to consider circles or square footings or any shaped rectangle, and then also a depth correction factor, which allowed us to correct for footings which are below the ground. So the basic equation is the same with these two additional parameters. And then over time, various other people have come along, Mayhoff, Brink-Hansen, and made slight improvements to those equations, included inclination factors and all kinds of sloping ground, and also the consideration of drained material as well. So at the end of all this, we have a mechanism for calculating the ultimate bearing capacity of a simple footing. But what do we do about settlements? Well, if we look back far enough, we can find the British standard at the time, or one of the earliest ones, which is BS 8004, published in 1986. And what does it say? Well, it says, you know, we just divide that ultimate capacity by a factor of 2 or 3. And you think, why are we doing that? Do we not know the strength of our soil to within a factor of 2 or 3? Have we got that much uncertainty? Do we not trust our theory enough to just, you know, use a large factor? Well, no, in essence, what if you read further on, it tells you that you could, by dividing by a factor of 2 or 3, your settlement of your footing will be something acceptable. So we didn't calculate settlement. We just calculated the ultimate capacity divided by a large number and hoped everything was going to be okay. And now, of course, we can do a simple example. If we consider a circular footing, 2 meters diameter, with sitting on a material with an undrained shear strength of 50 kPa, we can use Skempton's formula and calculate an ultimate capacity. We can divide that by 3 and get an allowable load on the footing. And then even I can do a Plaxis analysis and check what this means for circular footing. So this is the simple axisymmetric Plaxis analysis of that exact situation, and you get that load settlement curve for that particular soil stiffness. And would you believe it? Now this is impressive. I actually got spot on the theoretical capacity from my Plaxis analysis. What you notice is if you look at the allowable working load on that curve by dividing it by 3, what you're in essence getting is a settlement less than 5 millimeters at working load. So you haven't assessed the settlement directly. What you've done is you've calculated the ultimate divided by a factor of 3, and then everything's going to be okay. And of course, you're in the linear elastic part of the settlement. It's predictable, and the movements are small. Now, that's not to say that you couldn't back then calculate the settlement. As Hilary would have said, if she had time, there are various elastic solutions for calculating, or estimating at least, the settlement underneath the footing. Going back to Boussinesque's solution from the 19th century, going through to Mindlin calculations and Poulos and Davis in the 70s. But typically, I think it's fair to say, and I'm willing to be shot down on this, these weren't done on these calculations weren't typically done in calculations. People relied on ultimate capacities and factors of safety, perhaps because people didn't have confidence in the stiffness, which is obviously a key component in any of these calculations. I'm willing to be corrected on that. So once we have this simplified approach, as monitoring improved and case histories were published, we then started to collate together empirical databases which allowed us to estimate movements for various structures. And if we go to 1982, and I'm not sure this is the first publication, first mention of this, but O'Reilly and New in 1982, the first paper I could find that mentioned that the settlement above a tunnel can be calculated assuming a Gaussian settlement drop. So the shape of the settlement curve is the same shape as the Gaussian probability distribution curve, and it's essentially defined by 2 parameters, which is the trough width parameter and the volume loss. And the volume loss, if you like, is the amount which the ground around the tunnel contracts before the lining is in place, which is then reflected the same volume, or at least assumed to be the same volume of the settlement at the surface. And then you say, well, okay, so what's the parameters we need? Well, there's various publications over time. People have published back calculated volume loss for various projects. These are all in London clay, because obviously that's where most tunneling is done in the UK. But you can see that over time it's got slightly better, but typically the volume loss can be assumed to be between 0.2% and 1%. So with that information, you can go along and calculate settlement above any tunnel of any geometry at any depth you want and make a calculation of the settlement effect. So then that's tunnels. If we think about shafts, if we go to 1994, again, it's Dr. New, this time with a different co-author, Keith Bowers, in 1994. And based on the case history data from following the Heathrow collapse, they found that the settlement around a shaft could be expressed in a simple equation with a squared term as a function of the depth of the shaft, and then your distance away from the shaft. And then this is just a single case history that was used in that paper. But then in 2018, and Jamili Faustian with Robert Mayer and other researchers at Cambridge pulled together a whole load of other case history data from shafts in London conditions, and found that New and Bowers wasn't too bad, but there were a lot more finessing in terms of the effect on the shaft diameter as well. So by the mid-90s, we could do tunneling settlement, we could estimate the shaft excavation. This is without any theory as such. This is just using case history data to make predictions. And then if we go to retaining walls, we go to 2003, these curves were plotted for the first time in the serial report C580 and have since been slightly updated and republished in C760. But they're essentially pulling together a number of papers by people like Clough and O'Rourke, Thompson, who did Masters Imperial, and Fernie and Suckling, and pulling together all of the case histories on the installation effects and the excavation effects on the ground. And these curves, you can see that each one of those points is a different case history, a different distance from the ground, and normalizing the settlement as a function of either the wall depth or the excavation depth. And these curves have been used and abused on every project ever since to estimate movements around excavations. And they get criticized quite a lot as well, because people say, well, they're so conservative. Well, they're the lower bound of all the case history data, so they should be conservative, right? If you want to do better, then find the case within all that, which is most likely the one you're thinking about, and then use that if you want. But this is essentially a collection of case history data that allows you to make an estimate of the influence zone of your work, give you a first estimate on the settlement effects due to installation and then excavation. And, it would be great if we had more and more databases that allowed us to enrich this data. So once you've got your tunneling movements, you've got your shaft movements, you've got your excavation movements, your installation movements, there are software available that can take these simple relationships, add them all together, and give you an overall effect of a project, such as, for example, HS2 or Elizabeth Line or any of these sort of large urban projects. And this is not a sales pitch, but Oasis make one called XDisc, which is very easy to use. So we've talked about how it was done by proxy in the beginning, using strengths, capacities, and large factors of safety. We then went on to think about how empirical, using modern as monitoring data and case histories were published, using enriched empirical databases to make estimates of movements. But then, of course, the biggest advance in probably geotechnics in the last 100 years was numerical analysis and finite element analysis particularly. And trying to pin down exactly when this began is not easy. I found through the literature there was a publication in 1981 written by Naylor, Pandy, Simpson and Tabb called Finite Elements and Geotechnical Engineering. That would have been quite an academic paper, book, I suppose, which not many people would have picked up. Probably the biggest advance in the adoption of numerical analysis in the industry is 1999 with the release of version 7 of Plaxis. And you may say, why is version 7 significant? Well, it was the first Windows-based version of Plaxis that was available. Before that, it was all DOS. and you're young and looking at me going, whatever's DOS. But it was very, very difficult to use. So that was when I finished my undergraduate here. And I've just seen over the 25 years, gradual increased use of numerical analysis, and of course, particularly ubiquitous Plaxis. And when I was doing my PhD here, I was fortunate enough to work with Professor Potts, who was my PhD supervisor. And I was here at the time at which he was preparing and giving his Rankin lecture, which was the first Rankin lecture that focused solely on numerical analysis. And even in 2002, he was asking the question, is numerical analysis a virtual dream or a practical reality? And I implore anybody to pick up the geotechnique paper with that, because it's very illuminating in terms of the power of numerical analysis, but also the massive pitfalls of getting it wrong, which of course fed into the nickel highway, which you could talk about another day. So numerical analysis can essentially do, now at least, almost anything you want, provided you can correctly program the soil constitutive model, provided you can get reasonable parameters for that model. You can model the actual construction sequence, so it's no longer looking at number of case histories and drawing a line through them and using it. You can actually consider the exact construction sequence you're adopting. You can do 2D analysis or 3D analysis. You can capture time-dependent behavior, and that can be either consolidation or even creep in organic materials. Your soil behavior can be as complex or as simple as you want, depending on the quality of the data you have and how well calibrated it is. And that's a very important point. There is, the analysis can give you whatever you want, but is it, if it's meaningful is the question you have to ask yourself, and that requires validation and benchmarking. And that's not just, obviously the program does what it does, but it's so dependent upon your assumption and the parameters you put in. They require the validation and benchmarking. And the other thing is, whilst it's great to do these complicated analyses, it can give you a false sense of accuracy. It gives you a precise answer, but is it accurate is the question you've got to ask yourself. Is it telling you the thing that's important to your particular problem? Or are you just creating something with lots of pretty colors to impress your client? So over time, you can see we started off with strength-based approaches and elastic solutions. We then moved through the 70s and the 80s and into the noughties using empirical approaches. And then since around about the turn of the millennium, numerical analysis has really taken on a much more prevalent position in our everyday engineering. But what about the future? Now, this is my geotechnic wheel. John Berlin has his geotechnical triangle. I have a geotechnical wheel. I can't really claim the same role in the industry, but anyway. So if we think about how we do a design, what we do is we start off with parameter determination. Okay, so we do a ground investigation, we do some interpretation, we choose some values for our typical parameters, and we put them into an interpretive report. We then use them in our design and analysis. Probably these days, depending on where we are exactly, we probably have to do some movement predictions and impact assessments for neighboring properties or utilities or whatever. We then go to construction. We get some data from instrumentation and monitoring. And what we should be doing is then using that data and our predictions and back analyzing and calibrating our model. And then that calibration then goes back into our next project, our next parameter determination, and we create a virtual cycle of improvement and learning. And it's this cycle that created that improvement, if you like, from our movement predictions over time, from strength-based approaches to empirical-based approaches to advanced numerical analysis. So what does it mean for the future? Well, parameter determination, well, that can be processed and automated. We can get our AGS data from our ground investigation. We can import it directly into whatever software, and we can spit out geotechnical cross-sections, SPT plots in minutes. Okay, so that's quick. It can be automated. The design analysis, that can be automated. On HS2 with the Arup team, we were taking sections from a 3D BIM model, putting it directly into Plaxis and running a number of Plaxis cross-sections along the Houston and then stitching back together the 2D model to create a pseudo 3D model. So that can be automated. Our movement predictions, well, that can be taken directly from our numerical analysis, which we use in our design, right? So that's essentially part of the same process now. Construction, you know, I work for Langer Rook, so I have to talk about DFMA. So there is off-site manufacture, modularization of things, and bringing in geotechnics. You know, earthworks plant can be computer controlled by GPS, things like that. So construction can be automated. Instrumentation and monitoring, we use automatic total stations already. We can use INSAR, using satellite images to look at movements. We can use fiber optics and the Internet of Things. We can embed whatever sensors we want in our structures and get the information from it. And then back analysis and calibration. I'm just going to throw some terms out here, but you know, I'm too old to know what it really means. We could talk about artificial neural networks and real-time back analysis, which allows us to take our models used for design and prediction and automatically back analyze using the data from the monitoring to create a calibrated model. So my argument is that this is not the future, this is the present. This is where we are now, what we should be doing as an industry. So what is the actual future? There, I've said it. It's AI. Of course it's AI. If you think about where we all work, our firms have designed over the decades hundreds, if not thousands, of embedded retaining walls, piled foundations, whatever, and they're all sitting in a dusty box in a repository somewhere. If we could feed that information into an AI model, you can go away and learn how you did it, what the inputs were, what the outputs were, and then in the future you can just say, I've got a basement, it's 3 levels, it's in London, I've got 5 meters of made ground, what do I need? And it will give you the secant wall thickness, the bedment depth, the propping sequence, the construction sequence, and the drawings automatically. Is that a scary future? Well, there still has to be somebody who looks at it, right? Somebody has to check that it's reasonable and right. But we can automate that process and use the AI to produce something quicker. And it's inevitable. I mean, I think if I look back at some of the archive records I've had to look at over my career from the 70s and things like that, people were still doing method of slices by hand calculation, right? You find a handwritten calculation for slope stability checks. Now we would do it in seconds in a model. So process is the same. But it's made quicker. So we're expected to do more, and we're expected to do more and more often. Because if you had to redo that slope stability by hand because something changed, you'd be like, no, forget it. I'm not going through all that again. But because you can change it in the computer now, you would update it. So what's the consequence? I find a lot of truth in Dilbert, and you'll find that essentially a lot of your work will be replaced by AI, but there will still be roles for geotechnical engineers, but we will essentially be expected to become more efficient. And as he says, the reward for more efficiency is more work. So where were we? We've been through the whole sort of last 100 years of geotechnics about how strength-based approaches were used, empirical approaches developed using monitoring data, and then how numerical analysis has kind of taken over both routine design and ground movement predictions, and about the future. As engineers now, we have all of these tools at our fingertips. So what do? What's the important message? I like a quote from George Box, who was a British statistician, and he very wisely said, all models are wrong, but some are useful. And that's the message you need to take away. Don't believe any of these things. They're all wrong. There's something wrong about them. You, as an engineer, have to decide which ones are useful and when. So, thank you very much.
Thank you, Stuart.
You're staying up here?
Yeah. So
Here is your talk.
from the people online, you can ask your questions using Slido. People in person, you can just raise your hand. And so if you have any questions for, speakers. Can I have some help with the microphone, please?
Just give him that one.
Yeah.
I think that was.
Thank you. I have a question for Stuart. Stuart, excellent presentation, very well delivered, and some very key points, very well explained. I would add also for the key events over the last 100 years, also the seminal paper by Ken Fleming in 1992, which is probably one of the most influential geotechnique papers for the settlement of pile foundations as an observation. But I wanted to ask you, in terms of the AI, how do you think that will impact on the training and the learning of the future geotechnical engineers? And let's face it, most of the people in this room are the future. And how are we going to give them the opportunities to learn in the same way that we had good opportunities to learn? Thank you.
That's an impossible question. And I'll tell you why it's impossible. I'm lucky enough, I was sitting on the Industrial Advisory Board for Southampton University. And I guess it's the same here as well in all universities. As time goes on, knowledge gets bigger and bigger, right? We don't forget stuff. We learn more and more. And we need to pack more and more into the courses, which are the same duration with the same number of lectures in. So the question that all universities are asking themselves, I think, is what do we drop then? If we're going to have to teach our students about programming, AI, artificial neural networks, whatever all these fancy new terms are, what are we going to drop from the fundamentals that Hilary talked about, which we all need to know to get to that point? And that's the real challenge. I think, unfortunately, some of those fundamentals will drop away. Some of the rules of thumb. Do you need, like, for example, perhaps one thing you could do is we need to know about soil as a particulate material. We need to know about strength. Do we need to know about Boussinesq anymore? Does it matter? You don't need it, right? You could do an FE model. You spend a lot of time learning Boussinesq. I don't know. That's you maybe some stuff could be dropped, but it is a very difficult balance, and I don't envy the university that have to make that decision. So yeah, I don't know.
I'll ask a question. So you just responded to one of the few questions you had, but following, on this, how, even if we have, for example, numerical modeling capabilities, even advanced numerical modeling capabilities, how important is to still build on the fundamentals? For example, one thing you said about numerical modeling, you have this, you may have this sense, this false sense of accuracy. How is important to have to build on the fundamentals to understand if what more advanced techniques are telling you, if maybe checking with a very simple hand calculation what you're getting. So
yeah. I mean, I think
interaction.
Hey, case histories, and I implore everybody to write more case histories. Perhaps you don't think your case history is that interesting, but get it out there, write it in a paper and get it published, and we can collate them together into the larger case histories that formed those empirical databases we're talking about. And then they form our method, our ability, allow us to validate our numerical models. But there are serious things gone wrong with numerical models. And I'll mention again, Nickel Highway. That collapse and those deaths, I mean, I don't want to get legal here, we're not going to be sued, are we? But, that collapse was caused by somebody not understanding the difference of soft marine clays in Singapore versus stiff over-consolidated London clay, and whether or not you can, use effective strength parameters in order to calculate your undrained shear strength. That's what it came down to. You know, so it's important to remember the fundamentals. You don't want to sound like a stick in the mud and hark on about the past too much, because you need to move on, but they do remain important to some extent. Yeah, I don't know, Hilary, do you have any thoughts on that area?
Yeah, no, I definitely think that you know, numerical models, they're fantastic tools, but you know, they're only as good as what goes into them. And they all have to make assumptions, they all have to idealize SOAR behavior. So it's really important to understand what you're putting into the model and how that model is idealizing your SOAR behavior. And also think about the stress path you expect the material to go through. Think about what you expect the outcome to be, and that will you need those tools to be able to understand, is your model telling you the right answer, and then using that model to investigate, you know, variations, which it clearly can do very quickly. So yeah, I think more than it, or as much as ever, the skill of an engineer is needed, probably even more than ever, because it's so easy just to rely on the output of a beautiful computer program with beautiful plots. Yeah.
We have a question online, and I'll come back in a second. They're asking still about AI. Variation in ground is somewhat predictable, but can't all be done by AI. What do you think on AI creating ground models and its reliance for variable ground? I mean, that's addressed.
Why not? Why not? Why couldn't it? Why can't it learn all the designs you've done in the past, what the ground conditions are? You feed in your data from your current ground. I mean, I'm not saying this is the way it's going to go, but there's going to come some aspect of this. But I think it's going to be a little bit like ChatGPT, right? You ask ChatGPT a question, it gives you an answer, and you then spend a few hours correcting it. So maybe the AI will give you your first design pass, and then you will spend the next couple of hours correcting it. But it will do that first legwork for you. But I don't see any reason why it can't learn. I think they can learn.
Studies is really huge, because you know, many of us are in London, and London clay's been so well documented. You know, we understand it, we can get parameters, you know, we can use parameters without having done an investigation, for instance, certainly in preliminary stages. So but you move outside of London, and you're in an unfamiliar ground condition, you're looking around for papers that people have written on that particular geology, and so and you're necessarily conservative if you can't find enough empirical evidence. So I think it really is on us to publish and to monitor and to publish the results of that monitoring, so that whether it's AI or us, you know, we just learn, and because we have more information, more of that empirical information, we can produce, you know, we can optimize our designs in the future, which will be a more sustainable future, you know, with or without AI. Yeah.
Hi, thanks for the mic. Interesting presentation. My question is more related to Stuart's presentation as well. So we do mention about, you know, the historical and the future, but how do you think our current design standards and codes are dealing with it, and whether the codes will need to adapt on how we are designing things, like Eurocode 7, for example?
Yeah, I mean, I found it interesting looking back at that BS 8004 that it says just choose a number between 2 and 3. You know, it was left to you, the engineer, to decide how critical the structure was, how uncertain you were in the things, information you had, and you could choose a number 2 or 3. And you're thinking, like, if I was a hard-nosed businessman, why would I choose 3 if I can choose 2? You know, but it was left to you to decide. Eurocode 7 now is, of course, much more prescriptive, and it tells you exactly what number to use. And in the new generation, the second generation, it will allow you to tweak the number depending on the consequence class of a failure of that structure and the complexity. So I guess codes are they're there for guidance and not there for blind obedience, and that's something some people sometimes forget. You know, they are for blind obedience if your contract requires you to, but that's a separate thing. You know, so I can't see how any of the progression would affect what the codes would follow it. I don't. You know, you're addressing uncertainty and risk, aren't you? Whether you're
in ways, if you think of the bearing capacity calculation. Sorry. Yeah, if you think of the bearing capacity calculation, and we have our material factor that is quite high, and our load factor that is quite high as well. But if you actually do the settlement calculation, you know, you can allow that.
Yeah.
But I don't think the current code allows you to fail your ULS or like reduce your material factor.
Right. It's something I put up there is measuring performance-based design, and that's exactly where that's coming from. You know, do everything on serviceability, do everything based on the performance of the structure rather than partial factor. Yeah. So, but again, it goes back to reliance and your confidence in your movement predictions and the soil models that produce it, statistical models that produce it.
Thank you very much for the perfect presentations. I again have a question for AI. How do you see the future of soil investigations, the presence of AI, particularly laboratory testing? Because at the moment, AI is used for CPT results interpretation, but how about laboratory testing?
It all depends where you are, doesn't it? I suppose what uncertainty you have in the ground. I mean, problem is information is not shared, is it, freely across, not in this country anyway, across projects and clients. So we end up redoing investigations numerous times on the same sites and often not great quality. So we're essentially just doing it just for the sake of doing it, not necessarily for gaining any further information. So yeah, I'm not sure what the answer is to that question, to be honest. I mean, if we could collate all this information and again feed it into a learning algorithm, maybe we wouldn't need to do any. Maybe we'd do a few confirmatory things for our own peace of mind, but they wouldn't need to be exhaustive GI. But yeah, it's difficult, isn't it? You know. Well, I mean, there's too much data in some parts of the input. Yeah.
I mean, that again brings up the skill of the engineer in being able to specify the right testing and the appropriate testing, and understanding, you know, what those test results are telling us. So, you know, there's an onus on us as engineers to make sure that we are really being really efficient in what we specify and targeted. So the skill and the need is still there.
Session 6 will cover that.
Will it? Fine.
I'm pretty
Fine. It is now.
Apparently. But it will be covered in further sessions, whichever one it is.
Yes.
My question is for Stuart, again, AI based. I'm a geotechnical design engineer. I'm doing pile designs. Am I going to lose my job in 2030 due to AI based software for doing everything?
I can't talk for you specifically.
Anyone?
But I mean, piling is a great example. Because you could turn up with a CFA, you know, if you're relatively, let's future gaze, right? You turn up to your site with your CFA rig with all the readouts that the CFA rigs provide, and you drill your first pile. You get your you get your crowd and your force and your rotation speed and everything, which you can then correlate immediately to the soil parameters, which gives you your pile design for the next 100 piles that you do. That had kind of cut you out, but whether or not anybody would ever get there, I'm not sure. I think genuinely we'll just be expected to do more for less, quicker, exactly as it has happened over the last 30 years, frankly. It's just an further acceleration of that. But we're still, I mean, I don't know, the geotechnical community must be as big as it's ever been, I suppose, so we haven't lost our jobs necessarily, have we? Even though we're expected to do more and more.
We'll see in 10 years.
Yes, yes.
I have a question for Hilary. So say you interview a young geotechnical engineer tomorrow. Well, not tomorrow, let's say in a few years' time. What skills and knowledge do you expect to see in the new geotechnical engineers when you interview them? So you still want to see strong knowledge of fundamentals, or you want to see more, or what are you okay to compromise? What fields?
Well, what I think is that it depends whether that person's done the MSc course or an undergraduate course, and there's a big difference. So people who've done undergraduate courses, the geotechnical component may only have been one small component amidst lots of other subjects. So you don't necessarily expect that they, amongst everything, that they're particularly strong geotechnically, whereas perhaps someone who's done an MSc course, that's a bit different. I think enthusiasm and interest is really important. I think as Stuart was saying, our subjects is so wide now. But I also think that you don't have. You can join them up. If you to me, if someone, you can learn about different soil types for your whole life long. If you have those. You have that interest and to understand a soil behaviour, then you can apply that in lots of different contexts. And yes, I mean Python coding, programming, this is a huge area. Yeah, I don't really, clearly those skills are needed, but I think that people shouldn't, what I'm trying to say is I don't think people should feel that they've got to go down this road or this road or this road, because they're all connected. So they can, yes, they can be strong in one area, but it doesn't mean that they can't understand what's going on in the other areas. And we're teams. We have to join up. You need all these strengths. So I think, I haven't really answered that question, but I just think everything's connected. That's what I'm saying.
I would say time for the last question.
Hello, hi. I have a question for Hilary. So when we were discussing about the triaxial and the simple shear, then you mentioned about a volume change in one direction. So what do you mean by volume change in one direction?
Just explain.
Yeah, you were comparing about you said volume change in triaxial would be higher compared to the simple shear because the volume change would be in one.
Basically, if you imagine a triaxial situation or three-dimensional situation, volume change can happen in three directions. Whereas if you're in plane strain, a plane strain situation like behind a retaining wall or maybe a long strip footing, volume change can only happen in one direction, and therefore you can understand that dilation that's giving you your increase in friction would be higher for the plane strain, the more constrained situation, than for the three-dimensional situation. That's what I was
All right, thank you. And I have one question regarding the AI as well. So, like, for instance, like if we have designed something like based on the output which we have got from the AI, and if something of that sort happens, something like happens, so like can we like held responsible like AI? Like, can we blame AI for anything? Yeah. So it means like someone has to be there to take the responsibility, and we might not lose our jobs.
Yeah. Yeah, no, I think that's right. That's the parallel I would draw with AI at the moment is somebody needs to check it. We can use it to get 70% of the way there or something, but somebody needs to finish it and check it and take responsibility. Yeah.
Thank you.
Yeah. Oh yeah, he'll learn from his own mistakes as well. Yeah, once he gets sued.
So I'll I'll thank our speakers today for their presentations and their efforts. So
we would like to thank Ricardo as well for all his efforts sort of trying to pull us all together and input his ideas as well.
And so our gift is a sustainable gift. So it will be a gift card for plants.
A plant?
Yeah.
Wow.
Thank you.
We've got to keep it alive as well. Fantastic. Thank you very much.
So, so I'll conclude this session thanking again the sponsors. So there is food and drinks at east side bar. So basically you go out from Scampton building, turn left again Exhibition Road, turn right, and you can see the map. But you know, some few of us I think we're going. So future events. Tomorrow joint meeting with the BTS and EGGS about groundwater lowering for construction of the Hillsby Tunnel on the London to Birmingham Railway. Mike Crimes, Martin Preen, tomorrow the ICE. The next session of the MOGE discussion series will be on groundwater considerations. It will be chaired by Emily Riley, and the speakers will be Prof. Pori, Dr. Preen, and Mark Lee. And it will be in Leeds, University of Leeds.
And available
And
available online.
And available online, yeah. Wednesday, the 1st of May. Then 7th of May, BGA Southwest evening event will be on the HS2 Earthworks experiments, planning, data, and outcomes. Speakers, Simon Butler, Itziar Rojo, and Kevin Briggs. Sorry if I didn't pronounce the name well. And on the 16th of May, chalk characterization for driven pile behavior at chalk sites, Professor Jardine, Dr. Bink, and Dr. Buckley at the ICE. BGA annual conference and AGM on the 12th of June at ICE again, all day from 9 to 7. And save the date, 15th October, BGA 75th anniversary. Finally, the student membership, about the student membership, the students can now join the BGA for free. And that includes online access to ground engineering, discounts on GE and BGA sponsored events, and access to members area of the BGA website. So I'll bit dark. So thanks everyone. And sorry, before I forget, if you check again on the slide, there will be a feedback poll. So please, yeah. So if you can give feedback. Thank you.
Thank you very much.
Right.